In this video, we're going to practice finding the pH of a weak acid solution. So for both of these, go ahead and take this concentration, the Ka, and try and solve the pH of these weak acid solutions. Then unpause and come on back. All right, if you're back, well, let's start with A. I have 0.35 molar ammonium. So my ammonium is going to be in equilibrium with H plus and ammonia. My initial value was 0.35 and 0 and 0. I'm going to lose some of my acid. I'm going to create some of my base, my H plus. I'll eventually reach equilibrium. My concentrations, I'll have X amount, like whatever amount separated of my products, and I'll have my starting minus X of my starting material. X is likely very small. The Ka for ammonium is really tiny. Remember that if our concentration of our acid divided by our Ka is greater than about 400, we probably can simplify and just assume that minus X is too small to notice once we round the values. Well, my Ka is going to equal my H plus, my base, over my acid, which means 5.6 times 10 to the minus 10 is going to equal X times X all over 0.35. Multiply our 0.35 up, so 5.6 times 10 to the minus 10 times 0.35. 1.96 times 10 to the minus 10 equals X squared. Take the square root of both sides. X should equal 1.4 times 10 to the minus 5. Well, I want the pH. X, since we're in 1 liter solution, is our assumption. X is our molarity. So my pH is going to be equal to the negative log of 1.4 times 10 to the minus 5. My pH is going to be 4.854. We had 2 sig figs, so I got to keep 2 sig figs. 4.85. So our 0.35 molar ammonium solution has a pH of 4.85. Well, let's do our second solution here. 0.025 molar HAC, and it has a Ka of 1.8 times 10 to the minus 5. Same idea. We're going to lose some starting material. We're going to make some products. So our HAC is in equilibrium with H plus and AC minus. Our initial values, again, we're assuming this is in 1 liter. And so we're going to have 0.025 mole, no moles, and no moles. There's going to be a change. I'm going to lose some starting material. I'm going to make some product. I'll eventually reach equilibrium. 0.025 minus X, X, and X. As we set up our expression, 1.8 times 10 to the minus 5, our Ka has to equal our products over our reactants. Our product is H plus, so X at equilibrium. Our base is AC minus, so X at equilibrium. All that over, well, 0.025 minus X, but can we make the simplifying assumption here? Well, let's check our concentration. 0.025 acid divided by our Ka. If we check that, 1,388, yeah, that's greater than 400. So it's reasonable to make the simplifying assumption. We can assume that this is approximately 0.025 still. Multiply and rearrange. So we'll multiply 0.025 up. 4.5 times 10 to the minus 7 must equal X squared. Take the square root. 0.000671 is equal to X. which compared to 0.25, yeah, that's pretty down there. That's pretty small compared to 0.025. In fact, that's about 2.5%. As long as your error is less than 5%, we generally can ignore it. And so 0.000671 is about 2.5% of our starting value. And so forgetting to subtract it doesn't introduce too big an error. Well, this is our concentration of H+, so we can use it to solve the pH. Our pH must equal the negative log of 0.000671. Our pH is equal to 3.17. So even though acetic acid had a lower starting concentration than our ammonium, 0.025 versus 0.35, it actually is more acidic. Our pH is 3.17 versus 4.85, and we see that in the Ka values. 5.6 times 10 to the minus 10 versus 1.8 times 10 to the minus 5. I mean, just look at the exponents. Ammonium is 10 to the minus 10, where acetic acid is 10 to the minus 5. The larger your Ka value, the more products you must make. And so for the Ka for acetic acid to be 5 orders of magnitude larger than the Ka for ammonium, we must make a lot more products by comparison. And we see that in our pH. We get a rather large decrease in pH, which is more acidic.